Okay, let's look at some more reactions of epoxides. So one more reaction I wanted to show you from the strong nucleophile box of reactions. So keeping with that same substrate we looked at in the last video. We can also take, I was reading the name of this, acetylide anion. And we can react that with the epoxide ring. So second step, maybe we work it up with water. Yeah, with the exception of alcohols, generally you're working up with water. I know I had said conjugate acid in a previous video. But yeah, so you end up with this, and then obviously you'll get the other enantiomer as well. One thing that might strike you as weird about these reactions is if we look at the carbon here, if we look at this carbon here, right, that carbon's secondary. And usually acetylide anions and even strong bases like we saw in the other day, like we can add methoxide there as well, or they are more you can do SN2 type chemistry, or it's pretty much an SN2 reaction mechanism in ways that you normally wouldn't be able to. So usually if it's secondary, right, we would expect to see some beta elimination there. And maybe you'd expect to see some sort of other product like this after you worked it up. This would be called an allylic alcohol. But you don't actually see that. And this is just another weird feature of epoxides. We could try and rationalize why that is in a lot of different ways. One thing you can kind of think about is maybe some of that reactivity for SN2s are faster because if we look at this, the intersection where the antibonding orbital is going to be, we've got our antibonding orbital is going to be kind of like right there. You sort of almost have all of the groups that normally would cause steric hindrance are kind of folded back a little bit. So maybe you get a little bit better access to the antibonding orbital, which speeds up SN2 relative to E2. And so now SN2 can be competitive again in a reaction that it's typically not competitive in. The other thing you might consider is what the transition state you'd have to be in to get the anti-periplanar transition state for E2, what that looks like. I don't think that's a huge barrier, at least in this particular structure. So I'm thinking it has to do more with how the epoxide sort of folds back the oxygen group and maybe gives better access to the antibonding orbital. But if that's unsettling to you, that's just kind of the way it goes in organic chemistry. We make up a rule, and then 2 lectures later we have to create some sort of exception for it. And we always go back and we always rationalize based on sterics or electronics or something that we know about the mechanism or transition state. So epoxides are kind of unique. And you might want to call these reaction mechanisms, if you don't feel comfortable calling them SN2, you could call them SN2-like reactions. And we'll see some other weird behavior for them too. But the underlying thing, the underlying sort of principles that we learned for substitution and elimination still hold here. We still try and explain things in those terms. Okay, so these are all reactions, and we sort of show the stereochemistry for them is going to be anti, because you're going through this SN2 type reaction mechanism. What about the regio chemistry, though? So for these previous ones, if we look at the ones that we've already looked at, that carbon and that carbon are identical, so there is no regiochemical difference, and that's why we get 2 different enantiomers, but we always end up with the same product. If we look at something where, let's say we're looking at this molecule. Well, now we have a situation where this carbon is actually different from this carbon. And so if I were to use a nucleophile, let's go back to the one we started with. Let's say we're looking at methoxide. Methoxide could go in this direction, right? Or it could go in that direction and attack at that carbon. So which way does it go? For strong nucleophiles, they generally go to the less substituted carbon. Let me write that down. So the Regio Chemistry strong nucleophiles react at the less substituted carbon. And so yeah, the product that we get out of this is this, and then yeah, maybe you want to work that up with water or something to get rid of the alkoxide. But yeah, the main thing is that we have these two choices, and which one do we get? We get it the less substituted, and this shouldn't be super surprising, right? If this is really an SN2-like mechanism, then we expect the regiochemistry to be dictated by whatever has less steric hindrance. The less substituted carbon sort of falls in line with what we expect there. And if you look into the book, I can't remember if it's in our textbook, in some textbooks, they have more detailed rules around the regiochemistry. Well, I guess we'll get into a little bit of that with the acid. But for strong nucleophiles, they go towards the less substituted carbon. Okay. So what about other nucleophiles? Weak nucleophiles. So we looked at strong nucleophiles. So strong nucleophiles, those are going to be things like strong bases, methoxide, cyanide. You could use azide, for example. Any of the strong nucleophiles that we learned about in our last, or not our last chapter, but the chapter before that on a substitution elimination, could be used here to open up that ring. There's no reason to go through them exhaustively. That's sort of the benefit. That's sort of the benefit of that substitution elimination chapter, is that we don't have to exhaustively write every single reagent down. There's a trend that we're looking for there. All right, so weak nucleophiles. So what happens if I have something like this epoxide and I want to open it up, but instead of using methoxide, I put it in methanol. If I just let it sit in methanol, what are we kind of hoping for here? We're hoping for, some sort of SN1 type mechanism, because it's a bad nucleophile, and bad nucleophiles typically either undergo no reaction or they go through some sort of SN1-like mechanism. If we just leave it in methanol, we get, what is practically no reaction, something that's extremely slow. But if we put a drop of acid in there, so let's say you put a little bit of H2SO4 in there, some catalytic amount, then suddenly we can get ring opening here. And the mechanism is probably what you would hopefully predict. So if I put sulfuric acid into methanol, just like in water we form hydronium, in methanol we form some protonated version of the solvent, methonium, whatever. If you want to draw it directly from the sulfuric acid, that's fine too. But you got to use something to do the proton transfer. Don't just draw H plus and draw it coming out and doing that. That's not cool in my class, at least. And generally, it's kind of sloppy. So what I'm saying is, in the first step, I'm getting sidetracked. In the first step, you want to protonate this. The correct way to do it is probably to use this species. This is the absolute most technically correct way to do it. But sometimes you'll see people draw it, instead of showing the proton transfer from methanol, they'll show the proton transfer from the sulfuric acid itself. This is less correct, but it's still fine. So you could, instead of drawing it this way, you could draw it like this. And that's okay too. Probably the sulfuric acid isn't intact, right? Because it's a strong acid, it's going to break down. I'm saying the one thing that you don't want to do is sometimes you'll see people draw these kind of naked protons and show this going there and grabbing that. And this thing just isn't real, right? So the proton is not just floating around in solution. It's either part of the solvent or part of some other molecule where you get it from. It's never just kind of hanging out alone. That would be, an incredibly strong acid. Okay, so we're going to stick with this. Okay, so the first step is just to protonate, just like we've been doing, right? If we have an alcohol, we protonate. When we did the ether decomposition in HBr, we protonated. So we're going to protonate this thing. And that's going to take what is a not great leaving group. Okay, it was good enough if we were using a strong nucleophile, but now that we have a bad nucleophile, it's not enough. And we're going to turn it into a pretty good leaving group. So now we've got all this ring strain inside of this epoxide from the fact that it's confined to a triangle. And we've protonated the leaving group, so we've got this really, really reactive species. And now it doesn't matter that we have some really, it doesn't matter that our nucleophile is really crummy. The reactivity of the epoxide has been tuned up to the point where it's just going to open up, no problem. And so in this type of reaction, you'll notice I don't have to do any kind of workup because I'm already in acid, so I form the alcohol immediately. And you'll note that here, remember in the previous video, I was talking about not making these mistakes where you have a strong acid and then you have a strong base present. Here we have a strong acid, but if we look at the nucleophile, right, it's not a strong base. It's a very weak base, so it's okay to have those. So you can't have a methoxide, like if this was deprotonated, you can't have that together with a strong acid. But there's nothing wrong with having a strong acid in there. You just don't want to have a strong acid and a strong base present at the same time. Ooh, one thing I forgot here. If this proton is still stuck there, yeah, there's one last step here. Now I actually get to my product. Sorry about that. And now we're here, and of course I said this was catalytic, so not surprisingly we regenerate it for the last step. Okay, so that's sort of like a more of an SN1-ish type mechanism, even though you do have two molecules involved in the substitution part. We're going to see that it's actually kind of a hybrid of SN1 and SN2. So the stereochemistry you still see inversion. And in that sense, the reaction mechanism is SN2-like, just like the strong nucleophile version. Okay, so the stereochemistry is SN2-like. The regiochemistry, though, that is SN1-like. So here, the nucleophile attaches to the more substituted carbon. And so that's what I mean when I say this is SN1-like. So here the regiochemistry is SN1-like. So remember that SN1 and SN2 actually have pretty strict definitions. If it's going to be SN1, then so this part's SN1-like. So the regiochemistry is SN1-like. But the stereochemistry, right, that is SN2-like. So we can still kind of adhere to what we've learned about SN2 and SN1 reactions, but it's worth noting that during this mechanism, during this reaction, let's take a look at one. So if I have something with some stereochemistry, like this, and I add in methanol and sulfuric acid, we're going to get substitution, because of the regiochemistry, we're going to get substitution at the more substituted carbon, which is this one. So that carbon has more substitution on it, and so in that sense, it's sort of SN1-like. But we also see inversion of the stereochemistry. So note that we saw inversion here, and so in that sense, the stereochemistry is SN2-like. So it's not purely SN1 or SN2, the reaction. It's actually some intermediate in between those. And the reality is, if you go in and take a more advanced course, is that you'll see that there's not just SN1 and SN2. There's sort of a range of ways that the nucleophile can be involved in the rate determining step, and a range of ways the leaving group can be involved. So you can have things that are sort of on a scale of SN2 to SN1. But for us, all we're really worried about is the fact that we're getting a certain regiochemical and stereochemical outcome here. If you want to kind of rationalize this, though, a way to do that is we can draw out the mechanism and sort of think about what's going on there. So remember, we always fall back to electronics and sterics. So our first step is protonating the epoxide. Okay. So what's going on here? So if sterics were dominating, we would expect to actually see nucleophilic attack right there, but we don't see that. And what the reason is, or an explanation of why that is this bond that we've drawn here, it's not equal to this bond. What's really going on there is that, and I think some books draw like a resonance structure. I would dissuade you from doing that. What's really going on there is that I'm going to draw it really kind of bigger right here so we can take a good look at it. Okay, what's really going on here is that the each of these bonds start to get weak. Oops. Each of these bonds, there we go. Each of these bonds, once you protonate that oxygen, these bonds start to get pretty weak right here. And because they're getting weak, you're going to start to get charge buildup here and here. So if the bond was to completely break, let's say, like if it was actually an SN1 reaction, what you would see is something that looked like this. We had a full positive charge right there. So these electrons would pop up here, just like you see in an SN1 reaction, and you would get a full positive charge there. But because it's not a purely SN1 reaction mechanism, that bond doesn't completely break, but it kind of partially breaks. Both of them do. And because both of them partially break, what you end up seeing is a larger buildup of positive charge on the carbon that is more substituted. So this carbon here starts to build up a lot more positive charge because it's more able to stabilize it than this carbon over here. Okay? So one way you could kind of indicate that might be with these green blobs I'm putting here. So this here has a lot more positive charge than this does, because this one can't stabilize its carbocation quite as well. And because it has more positive charge on it, it's more reactive to nucleophilic attack. And that is our explanation as far as why we get it at the more substituted carbon. So what's the rationale here as far as why it reacts to the substituted carbon? It's that when you protonate the oxygen, sterics become less important than electronics. And the electronics dictate that there's going to be a larger partial positive charge on the more substituted carbon. But because the leaving group doesn't fully depart and it's still kind of attached there, you actually still see the same stereochemical outcome here. Which is that you get inversion here. And then, of course, we have this last little step where we deprotonate, which should hopefully be becoming more familiar for you guys. So yeah, in our substitution elimination chapter, I kept saying again and again, I was like, if you want to use a flowchart to solve problems, that's fine. If you're trying to predict what the reactions and stuff are going to be. The real lessons that you wanted to carry with you, though, are these arguments about sterics and electronics, and trying to be able to think in those terms. And we can see here that things are a lot more complicated than they seem at first, or the way they're presented in that chapter. Sometimes you have both of those mechanisms sort of operating simultaneously, and we have to kind of go and do a deep dive to rationalize why the hell one thing's happening versus another.